So I'm Tony Vellum, Anthony Vellum, not to be confused with Anthony Vallone with the beard. Turns out we were both physics majors, both from the East Coast. My first job at Google was to take over his job, which really confused people, so I had to change my name, so just call me Tony. Usually when you see it in print, I use Anthony. Thanks for having me back. After I heard all the stats the last 2 days, I feel particularly honored to have actually been selected to speak this year. 2 years I spoke about sort of the budding cloud. Nobody really knew what it was. And then last year I got to be the jokester. So I try to add humor. You're free to laugh. If it's not funny, don't laugh. But if it's funny, you can laugh. And as I looked back at sort of the past talks that I had done, the one thing I noticed about myself is, I had blue and orange, and now I have gray. But for me, I kept looking at these pictures, and I just noticed my hairline was moving back. So I might not put these pictures again. So what do I do? I actually work here in Kirkland. I literally work right across the street on the second floor. I head up the cloud performance team, and my job is to make the most performant and the most price performant cloud in the industry. And in order to do this, we have to measure. We have to know where we are. We have to know how the landscape looks. And it takes a lot of automation. And so what I'm going to do today is take you through, how did we come up with the automation? What are we doing to evolve it? I'll try some demos here at the end, and if all goes well and you aren't using all the Wi-Fi, I'll actually be able to run something, and it'll be good. So here's the brief overview of what I'm going to do, and an overview is good because I'm known to talk fast, so thanks to the transcribers. So I'm going to give you a brief overview of cloud and benchmarking and give you some of the definitions. I'm going to go through a history where I parallel the sort of coming of cloud computing side by side with how benchmarking has evolved over the years and what's happened there. Then I'm going to tell you why we're sort of off base in what we've been looking at so far with cloud. If all goes well, you'll see a really cool demo, and then we'll wrap it up. So with that, what is cloud? Cloud is a word we've all heard, and honestly, there's only one person who's been able to explain what cloud is. And has the most accurate definition, and that is this guy here, Eric Schmidt, where he says, I don't know what cloud computing is, but I know it's a marketing term. Perhaps quite accurate, but for our purposes, I want to give you a little bit more context of what I'm talking about. So we've been in this transition over the last couple of years, and we're still in the very early days of this, where we're sort of taking the workloads that we used to run in dedicated and dedicated data centers or workstations under our desk. So instead of running on our local networks and our local infrastructure, we're starting to move them into the cloud and going over the internet in order to access resources. And by resources, I mean things like machines. That's Compute Engine here for Google. Storage, where you have object storage, put a file in the cloud, pull a file out of the cloud, do some sort of manipulation. There are really fast and rapid services like key value pair services, which are important to building websites, where you have a key and a value like data store, and these are really fast, and this is sort of infrastructure-y. And the picture that I'm showing here is pretty different than what we're most used to looking at, which is when cloud is often talked about, it's talked about as infrastructure as a service, platform as a service, and software as a service, this tiered pyramid of layered things. And that used to be true, but not so much anymore. So for example, Compute Engine is virtual machines in the cloud, and this would be considered infrastructure as a service, except that there's this ability to dynamically provision and deprovision machines on the fly. And so is this platform as a service, or is this infrastructure? And so what you see is this blending of these ideas in order to make all of our job, quite honestly, super easy, where we can build scalable infrastructure in hours and days instead of months and years. And so at Google, we look at cloud computing like this. We look at it as compute. There's things you're going to compute on, whether these are App Engine apps, things you're serving for your platform, or whether you're serving them from a VM. We think of this as the compute that you have. We think about it as storage across database and these key value pairs and object stores. If you really stand back at a 10-foot level, you really can see storage is storage. Bytes are going in, they persist, and we can get them out later. And then we have these services that help connect all of these other pieces and give you extra capabilities. Like endpoints allows you to convey messages into the cloud and out of the cloud and do things for you. And services like BigQuery allow you to do massively parallel query on hundreds and hundreds of terabytes of data in seconds. And so for Google, cloud is really this set of services that work together to solve a particular problem. Benchmarking. Let's take a quick look at the definition here. So Wikipedia, one of my favorite services. I definitely donate to this frequently, and I use it. So benchmarking. So benchmarking here is defined as the act of running a program in order to get a relative measure of performance, to get some number about how it's acting relative to something else. Well, this is a technical definition. I think a more astute definition might look like this. Which is lies, damn lies, and benchmarks. How do we find the truth about the performance? And so hopefully I'm going to give you some truth about the cloud performance and how to fairly look at cloud and how to measure it. So let's go through our history here. Cloud started long before any of us, or most of us, were likely alive. 1961, this is the really early days. John McCarthy, it's often said he opined that one day computing would be a public utility. This means you could turn it on or turn it off, and you only pay for what you use. That was a really brilliant observation in a world in which it was still a single mainframe at a university or a particular center. And in the 60s, you sort of had this evolution of technology as well. So we had this, the microprocessors came about. We started to think about how we connect computers. But on the benchmarking side, we needed a way to measure these platforms in order to know, is one better than the other? And the reason why this mattered is if you're going to buy a $1 million machine, you want to make sure that it's very cost efficient for the type of computation you need. And so here you see the advent of really early benchmarks like the Gibson Mix, ADP, and PCM, which were in the 1950s to 1971. And the first benchmarks basically look like this. There were instructions that computers would run for you. They did some statistics. They took all these different programs that were run. They figured out which operations were most frequently used. And from that, they created a distribution, a very sensible thing to do. And then they would just run this distribution of instructions over and over and get some measure of what performance looks like. And so here you can see, in this particular example, the most used instruction was a floating point add and subtract, which probably tells us the early computers were doing some sort of scientific computing because of the floating point. If it was financial, it would have been some sort of fixed point notation, which was used early on. A lot of the data that I have in the slides come from this site, Roy Longbottom. He was a UK assessment, I would call him a researcher, for the UK government. And the government there would collect all these stats about data, and he published all of these metrics. So I turned them into graphs. So I want to give him credit because he has some amazing data out on his site. And so what does this data look like? This data looks like this. So for the Gibson Mix, it was actually run, from the early days from when it was first invented, all the way up until about the, mid-70s. And here you have some really interesting things that show up in the data points. You have Moore's Law. You can see Moore's Law sort of showing up in the progression where, the data is kind of going up and up. But you have something else that's interesting in this Gibson Mix. And by the way, this KIPS, K-I-P-S, is kilo instructions per second. So that was like thousands of instructions per second. And so you see these points that float above the graph, and I have these arrows that say error or ingenuity. And my guess is this is the first time we started to lie with benchmarks. Some really bright engineer, she figured out, hey, we could optimize like this, and if we run the control mix like this, we can make our platform look astoundingly great. And the fact that it's so far off of this Moore's Law curve, I don't know, it could have just been an error in the data. My guess is ingenuity. Which takes us into the 70s and 80s. So if the early part was around like instruction sets and mainframes, the 70s and 80s were really about this growth of ubiquitous computing around networks. And so we saw the advent of ARPANET, and so in government and universities, we start connecting up machines and mainframes, and we start to get this notion of using resources at a distance, kind of. They weren't quite used that way yet, but the thinking was there to do it. In the 80s, for sure, we had all kinds of consumer services, bulletin boards, BBS, things were connecting up. We started even talking about how do we put groups of machines together. The benchmarking world was equally interesting. So in 1972, one of the sort of the next generation benchmark called Whetstone was invented. And it was really trying to get away from this instruction set mix and computation that was going on at the time and say, well, we have all these languages. You could program in any language. How do we assess how platforms are doing with particular languages? And so that progressed for a while, but you can imagine there's a lot of complexity when you think about how do you compare Java and C++ even today. It's more of more about the platform underneath. We also saw early HPC, so high performance computing, parallel processing type workloads like LinPack, which were doing big Gaussian eliminations, trying to find eigenvectors. Is your bridge going to fall down? And so they were trying to assess how good is a platform at solving these types of problems. As a joke on Whetstone, there was an evolution in benchmarks from the 70s to 80s, which was called Drystone. And Drystone, so you get it? Whetstone, Drystone? Yeah, okay. And so Drystone was this evolution, and what they were realizing is you can't just look at algorithmic computation. A lot of what we're doing is memory access. And so Drystone really tried to add in pointer indirection and memory gathering as part of the computation. And you'll see why this was so important in a slide or two. Along the same lines, we have graphics. Graphics is sort of starting the bud in the 80s and getting more ubiquitous. People have figured out how to optimize for Drystone, so then suddenly you have Drystone 2.0 because that ingenuity shows back up. And so let's take a look at how this looks in the data. So Whetstone. So that was the original. One thing you learn about benchmarks run for a really long time. You think that they die, but for some reason they seem to have a long life. And so Whetstone was run literally from the 60s, even till today you can go find results of people trying to run a Whetstone benchmark. Typically now you'll see other benchmarks that are there, and I'll show this in a slide or two. What was interesting about this data, though, is the UK really looked at mainframes in this period. And mainframes are important because of this evolution towards cloud, but they literally just stopped running it. So sometime in the 90s, mainframes are dead. Long live the PC and connected systems, and it grows up from that point on. And so we see this transition from the blue dots to the red dots. Also on this graph, I threw in there, when Google was founded, so computation wasn't all that powerful at the bottom. And then when EC2 was founded, you see computation was much more powerful when the first cloud services were launched to the public. But not only were we having this evolution of benchmarks and this move from mainframes to sort of more workstation type machines, which by the way, at that time period were $55,000 a piece to just stick this thing under your desk. It was quite expensive. We had this evolution in processor technology. And so here I have a graph showing why this was important. So this graph here basically shows Moore's law for computation, which is the red line, which is the steep line that goes up. And there's another law, I can't remember what it is. It's not Moore's law, but a very similar one for memory where it's not quite as steep of a curve. And we hit this inflection point sometime in the 80s where suddenly processors can process data faster than we can stick it into the processor. And so if you look at this graph, can anyone tell me the first time an L1 cache appeared in the platforms? Anyone? Yeah, right around 1990. Right around, if you go back and look, the first time we see Intel processors is right around the end of the 80s. And the reason they had to do this is because they had to have some way to keep data close to the processor and make it fast. And so we have this evolution not only in processors, but we have this evolution in how we think about systems. And so before we thought about systems as islands, we'd put our computation on them, we'd run it really fast, we'd get our results. But in 1985, you start to see papers talking about distributed applications and why aren't these things coming about? And the big Achilles heel at the time was the network. So to have cloud, I often say there's only 3 things that matter in cloud. You ready? Networking, networking, networking. Without a network, there is no cloud. And here they're sort of recognizing the fact that if we can get fast networks, we can move things from where they are now in terms of computation and what are running into a remote location. And so this was sort of an interesting paper. Well, this led into this whole series in the 90s around MPI computation. So MPI is message passing interface. It's a way to write distributed applications in a cluster. It uses multiple machines. It makes it much easier to do this. Used in scientific computing, and so you see things like MPI come about. PVM actually had happened. It was called parallel virtual machines. It was really pulling also clusters of machines together. That happened in like 1989. And then you see Beowulf clusters coming in for Linux. Linux was sort of taking off, and they had this notion of, let's just create clustered computers. So why do we need a mainframe if I can get the same amount of computation for a tenth the price? And so this happens all throughout the 90s, and at the end, I'm sorry, Ramith, I'm going to try your name. Ramith K. Chalapa has the first definition of cloud computing. And so if we look back, John McCarthy talked about having this elasticity property and utility. Ramith is often cited as the first person to actually put a definition to cloud computing. On the benchmarking side, things were a complete mess. We had databases, they were growing, data was outgrowing what we could consume. We didn't know how to measure who was better. Was it Oracle? Was it Microsoft? Was it Sybase? Who had the best database? DB2. There were many databases. Well, the group of individuals that were doing a lot of critical thinking about this came together. There's a conference that happens every couple of years where people come and talk about transactions and computation, but out of this series of conferences came something called TPCC. This was one of the first well-established database benchmarks led by a guy named John Gray, and this put order to chaos. And so this sort of plays into my idea of understanding cloud and measuring cloud as a bit of chaos. And so how do we put order to it? Well, the way they did this with databases was to establish a benchmark. And by the way, TPCC, 20 plus years later is still highly used and cited. It's been tried to be displaced by E and others. It just never happened. But C is really OLAP. This was transaction processing. We still buy stuff, and so these are still relevant benchmarks. Video sort of is growing up, and you see early sort of spec benchmarks. So Spec 92 is actually Spec's first computation benchmark. And this is where you see yet another transition in benchmarks where you move from trying to measure instructions to sort of this language thingy, to sort of looking at other types of attributes about the machine and memory, to sort of spec, which is saying, maybe it's the workloads that matter. Maybe these micro primitives aren't giving us enough information. And so in Spec 92, it really was around like Lisp and C and a couple of other things. But by Spec 95, which was probably one of the most popular spec benchmarks, was really around getting to other types of workloads like Maxwell equations, Gaussian elimination, water flows, mesh topologies, and even interpreted languages like Perl show up in here as a measure. But we're seeing other transitions that were happening throughout this time period. And so you think about networking, right? Networking, the only three things that matter in cloud. Well, it turns out in 2006, we had actually ratified networking standards for 10 gigabit networks. But here we are many years later, about to 8, and who here has a 10 gigabit network at home? Anybody? Nobody? Who has a 1 gigabit network at home? A few of you? You're very lucky. I wish Google Fiber would come to my neighborhood. But you start to see like gigabit. And so we've had the technology around networking. It was available in server rooms. It's being used. But there's enough networking capacity today to these data centers that it's quite usable. It will be awesome when we all have 1 gig and 10 gig connections everywhere. Video benchmarks continue to progress. Not quite as important to cloud. There are some workloads, AI or other workloads that make use of GPUs. What's really interesting about graphics is it was one of the places where the most ingenuity around benchmarking happened. And you see these amazing points where suddenly, they go straight up off this curve of progression, which is pretty amazing. And so this group really figured it out. The other group that's really figured out benchmarking is mobile phones. So we go from the 90s, we go to the 2000s. So we have this progression, right? We're seeing benchmarks come about. We're seeing the workloads change. We're changing how we measure. We're getting closer to what could be cloud. But we had to have some other things happen, which was the internet. Internet comes about. We have further progressions of things that help us build scalable applications, like Memcache is born in 2003. We have Eric Schmidt starting to actually talk about cloud computing for Google. And then you have one of Google's first cloud products, which is App Engine, and it comes out in 2008. On the benchmarking side, there's a pretty interesting progression, but the two things that I'll point out here are, one is HPL. So you remember back in the 70s, we were talking about LinPack, and this was single machine Gaussian elimination. Suddenly we're in the 2000s, and now we're talking about HPL, which is clustered machines doing Gaussian elimination computation. So we're scaling this out. The other thing that's interesting here is vConsolidate. This was one of the first virtualization benchmarks to show up, done by Intel. And then also Hadoop. So we're furthering this notion of clusters of computers and looking for ways to measure them. The way this looks in the data is sort of like this, and it forced us into it. So computing forever, Moore's Law helped us out. We had this completely incrementing computation. None of us had to do any work, and our machines would get faster, and thus our applications would get faster. And if anybody played Lode Runner when it first came out, the little dude would sort of move. And then I got like a 40 megahertz machine, and the dude just ran like this all over the screen. But things just got faster automatically. Well, if you look at this blue line in the middle, you see that it sort of goes up and to the right, and then it humps over. And this was processor speeds. And so while each core in a processor had always gotten faster, suddenly they weren't getting faster. And then the way Moore's Law sort of transcribed is we got multi-core platforms. So 2-core, 4-core, 8-core in a single processor package. But this means we had to get much smarter about writing parallel algorithms and parallel computations. And this sets the stage for cloud, which is inherently parallel, because you can get multiple machines, connect them together in virtual networks, and run workloads on it. And so right around 2006, this is where we're going. So now we enter the 2000s, and we're almost to this decade. But well, I guess we're in our decade now. So 2010, we have the progression of cloud products. And so you can see our icons are sort of growing up here. New things are showing up. Compute Engine with these sort of colorful brackets are there, our stacked computation, SQL's out there, and we have all this computation that's there. If you look at the benchmarking side, what's fascinating about this period, it's the first time ever that a workload that had been traditionally run in a data center, sorting, suddenly was more efficient in the cloud. And so MapR went out and ran a computation. In minutes, they spun up 4,000 cores in the cloud, ran a sort of, ran a terasort, so a big sort, in under a minute. This is the first time this ever happened. And suddenly we hit this point where computation in the cloud was now faster than what you could spend tens of millions of dollars to build yourself. And so this was pretty important. Well, the other thing that you can notice in this time period is Google progressed. You can tell when the really cool icons come out just how important cloud is. So one of the things you can do if you want to try the Google Cloud, cloud.google.com, it's a top-level domain. You can just go log in, spin up VMs. This is sort of the whole suite, everything from translation and analytics to computation. So it has also grown up. And having a more complete set of services is important to moving workloads into the cloud. But I'm here to tell you, the way we have measured things for over 50 years is about to fall apart for us. And here's why. The way we've often looked at measurement is like this. You can think of this as X unit, Tony unit, whatever unit. When it comes down to measuring things, we all generally fall into a very similar pattern. If you're going to go benchmark something, you have to have things set up. And so this is sort of the setup phase of what we're doing. So you have a setup phase. The next thing you're going to do when you benchmark is you warm up. You're going to go run a bunch of queries. You're going to go run some computations, send some networking packets, store some bits on a disk. You're going to warm things up, make sure the system is really ready. Okay? Then you might have some sort of pre-execute phase, which is not quite what you want to measure, but it's not really warm up, but it's just getting things ready to sort of collect and measure. Might be measurement steps. Then we execute things. And we execute for minutes or hours or days, whatever it is, trying to really get a good measurement of what is this. And the reason why we want to know what this is we're trying to predict if we go build this new architecture that we have for our application or our automation or whatever it is we're building, is it going to scale to meet our user demand, what customers want from us, the way we want the system to work? And so we spend time trying to figure out what are things that look similar to my application, and how do I go measure these things on this new architecture platform so that I can project if I'll be successful or not. And so we spend a lot of time on execute. Well, then we're done with execute. We've got our numbers. We do some cleanup. We tear all the resources down, and we publish the results somewhere. So we put the results out. So these are the measurement steps. Can anybody tell me what's wrong here for cloud? What happened?
You're not accounting for network bandwidth and caching the time to spin things up, resources you need.
Bingo. So I'm going to key off the second part. So the two things that were said is, A, we're not accounting for networking, maybe. But the second thing is we're not accounting for spinning up things or spinning them down. So if networking is the most important thing about cloud, the second thing that's the most important is elasticity, elasticity, elasticity. And what I mean by that is it's a utility. I turn it on, I pay for it. I turn it off, I don't pay for it. Guess what we're not measuring here? We're not measuring the cost of provisioning and deprovisioning resources. We're only measuring this very tight inner loop of, boop, here's how fast networking is, and we're done. But if it took you 2 days to get the machine spun up, you run this computation for a couple of minutes, and then you tear it all down, that's not very efficient. And so what you need is a system that's very, you need a system of measurement that accounts for this most important property. So thank you. So here it is. We've been looking at the wrong things. And so if the measurements you typically look at when assessing cloud providers is only this really tight inner loop, you're missing an important part of the computation, which is how fast can you get what you need and how fast can you give it back so you stop paying for it. That's an important part of the equation. So the things that we want to measure, though, as part of this execution, in addition to this elasticity property, there's 4 core properties. Throughput latency, these are pretty standard. Overhead. Overhead is important in the virtualization world because the providers are going to use some amount of your resources to support whatever thingy you get. So if it's a virtual machine, there's probably some amount of computation that's being borrowed to do storage or networking or something else in the cloud. And so you want to sort of pay attention to overhead. And the other part is cost. Cost. Cloud, it's awesome, right? Everything is sort of billed by the hour. It's 10 cents an hour, whatever it is. At the end of the month, sometimes it feels a little bit like death by credit card. You get all these little transactions, and at the end, you're like, whoa, where did that $100 bill come from? And so cost matters here. And this is why elasticity matters with cost, because if you can provision and deprovision, you can control your cost. If you're in this mode of just spin up resources in the cloud and leave them forever, you may be better off doing something else. But there's definitely benefit to somebody else hosting it, and it could get geolocated. There's lots of benefit. But you should think about the elasticity property so that you can really make the most of it. And this is particularly important for a lot of the conversations that were had here today and will be held tomorrow, or later this afternoon. So what are we doing? This is the interesting part. What we don't want to do is we don't want to go out and say, in order to get a fair assessment of cloud, we should take everything from everywhere that's ever been done and go run it and get a number. That wouldn't really serve us well. There is such a thing as too much choice is a horrible choice. And so you want to be very selective about why are you choosing the things that you're choosing. And so one of the first properties as we looked at tackling this problem for Google was how do we keep things minimal? What types of workloads are important? And there are even really important ones on here that I don't have, like SaaSbench, which measures, other types of systems in the cloud around database and, managing people and that kind of stuff. But there's lots of benchmarks. So the first thing we had to do is think about how do we keep things minimal? What do we want to focus on? Well, for sure, that elasticity property is going to be a part of anything that we do and measure. But we have to choose other workloads. And I'll show you some examples in the demo. The second thing we have been thinking about is the things that are being built today are unlike the things we saw in the past. Games like Candy Crush, when these are $1 billion game, it looks very simple to us on our phone. That game doesn't exist without a huge amount of telemetry going to a back end and figuring out if Mary, does she want to buy the blue, have the little blue crystals show up or the little green crystals? And we find out that if we put more blue in this thing, she clicks on blue more, so we're going to put more blue on hers, and this will lead her to play the game longer and lead to some sort of impression on an ad or whatever it is to monetize. Or, hey, maybe John likes the pink crystals, so we're going to sell the pink crystals to John and say, hey, for 10 cents more, we'll put pink crystals in there, and this creates, delightment for us, right? It's trying to engage us. But what this takes are massively parallel systems in the back doing computations against streams of data. There's millions of users streaming, all this telemetry in. It goes into these big back-end cloud systems, and they get crunched on, right, to sort of figure this out. So the thing we have to think about around workloads are the traditional workloads really going to address how we compare clouds or think about how we might compare clouds? And so we've looked across, Hadoop workloads, which are, popular for handling these types of computations and streams and running benchmarks. We've looked at, how might things get stored in the cloud. Object stores are very different than file systems. They're write-only typically. They have no locking. There's all kinds of things that you don't get. You get a shared namespace, which is great, but they're different. And we're sort of looking out around how are the topology of the things that we're building actually fundamentally changing. And so are things running in single zones or across zones? So if you think about somebody like Netflix, Netflix doesn't ever want to see a failure. So for them, they're stated as using a cloud provider. They put everything in the cloud. Everything that streams comes from a cloud provider somewhere. But they talk about, we need to be in multiple regions of the world and multiple zones. So if one goes down, we can keep playing videos, and half of America won't go up in arms because they can't watch Pinkie Pie at 8 o'clock in the morning. And if anybody has kids, you'll appreciate that comment. There are other factors in terms of building benchmarks or building ways to measure and analyze things. We have really paid attention to what's going on in terms of blogs. What are all of you talking about? What is technical sales talking about? Who's coming to the cloud? Why are they coming to the cloud? How do we make everybody come to the cloud? My personal opinion about the cloud is we will get to the limits of human imagination for practically zero cost. That's why I work on cloud. I think that is the future. We look at the industry analysts. Where are they going? Third-party reports. And so we're trying to get all this data about what's important. It's amazingly hard to figure out what's important. But other places we look are like, what do the providers say about themselves? What do we want? Well, what I want is the defaults. You install something, you run it, it runs great, you do nothing. I'm kind of lazy that way. I think it's very hard to figure out how to tune a database or tune some NoSQL cache. We shouldn't have to do that. It should just be done. But we also want to pick things that are very transparent to the industry. So if you're going to measure something, you want people to understand why you're measuring what you're measuring and how it's being measured. And so we looked at a set of properties that we had around benchmarks we wanted to look at for ourselves. Ease of use was important. Developers, we hate sort of running stuff. So if we can make it easy, we'll run it more. We wanted them to be free to use. It makes it easier. We wanted to be relevant to our customers. And so we had all these sets of properties in this third column here that we were going after. And then, of course, we want to stick with our methodology. The methodology has to be really adhered to. Measure everything, measure the elasticity, and just keep, rinse, lather, and repeat over and over. So we're going to stick with our methodology that we talked about. We actually built a system internally for us, and I'll show you a demo of it, where we measure the cloud, we look at the provisioning aspects and so forth. We have ways of processing and sort of passing results around. We actually use our own products. We built our data repository on BigQuery. We have billions of data points of performance measurement, and we actually run BigQuery to boil this all down and give us a single answer in computation. Nothing happens without pretty visualizations. As engineers, it's hard to look at tables. So when you see graphs, they really help out. So we have systems to look at graphing. And this top left graph here is networking improvements over the last year for Google. We went from like 1,000, 1 gig that we could sustain VM to VM throughput, all the way up to now, which isn't even shown here, all the way up to, well, I'll leave that to the Cloud Live event next week. If you haven't registered for the Cloud Live to see it online, you should definitely watch the Cloud Live event. But let's just say what Google can do with networking is impressive. So with that, I'm going to fearlessly attempt a demo. Let's see if I can get this working. All right, looks good. Look at that. You can tell I'm very creative in naming my machines, Vellum-MacBook Air. My last one was Virus and SpamNet, but I got so many emails from security over that, I decided when I upgraded, probably not such a good idea. All right, so what I'm going to do is I'm going to show you an example of basically measuring provisioning time in the Google Cloud. And so we have this tool called Artemis. It's our internal benchmarking tool. This is what we really use in order to look at measurement. And so what you see here is it's going to kick off. And you'll notice a couple of things as this runs. One is I use my own project. It's targeted at cloud equals GCP. That's Google Cloud Platform. The benchmark that it's running is just a basic boot test. Let me go boot a VM in the cloud. In fact, this one's booting up in US Central, so somewhere in Iowa, little electrons are flowing into a data center to give me a machine. It's going to boot, basically do a little quick check on the machine, and then tear it down. And so one of the things that we did with this tool, though, that I think was important is we built a tool that acts like you, the human. And if you look at the instructions that are running here, it's running this tool called GCUtil. This is really the tool we provide to everybody for cloud, for getting resources in the cloud. There's actually a next-gen one called gcloud. I just didn't have time to update this for this particular discussion. But these are the command line tools. And so what's cool about this is you literally get, as a developer, a tester, an engineer, instructions that you can just copy and paste instruction by instruction and rerun the benchmark. And so when I talk about being transparent about what's happening, this is what I mean about let's be this transparent. Here's exactly what I'm doing. And so here you can see as it spins up, it's targeting things like, let me go try to sudo apt-get, and so there's a sudo apt-get update. It's running an update inside the VM. Let me get all the latest bits that are out there. I run an update. And then after it does the update, it starts to tear things down. And in fact, we actually have the boot time measurement encoded in this blob where it says boot time 39 seconds. But guess what we're waiting for now? What are we waiting for? Yeah, the teardown, deprovisioning. Did you see how fast provisioning was? It was fast. We got a VM like that. The teardown, a little bit longer. This is where we're making decisions. Do you want to delete your disk? If you really want to delete your disk, we better make sure that that data is really gone. We do all kinds of encryption in the cloud to make sure your data is safe and secure. And so here we're tearing things down. You can see the deprovisioning step. Delete the firewall, delete the disk, delete the instance. And here in about a couple seconds, we see how long this took. So it literally took us from the time I ran the first command to all the way to being able to log into the machine and doing the apt-get update took 39 seconds. And for Google, if you run 1 or 1,000 of these, guess what? It's not that much different. Can you imagine what you could do with 1,000 machines in like 39 seconds? So one thing I usually tell people when they come to Google and they ask me, what's the hardest thing about working at Google? My personal opinion is the hardest thing about working at Google is it's terrifying to think everybody has a supercomputer at their fingertips, and how am I going to make good use of this resource? It really puts you at the limits of your imagination, as I mentioned before. But our whole end-to-end thing really took about 2 minutes, 127 seconds. I round down, I'm a perf guy, right? It looks better. 2 minutes? Okay. Okay. All right, so that was one example. The other thing we did with our tool is we recognize whenever you have an automation system, you have to think in incremental parts. Like, how are engineers going to use this tool? So we could run this. It takes a while. But there may be things that we're doing. We may be tweaking experiments on like virtual machines. There may be flags we're flipping, trying to say, hey, can we change behavior in the network? Can we change behaviors to storage? How does this look? Well, you don't want to always have to wait for all these resources to provision and deprovision. When you give your final measurement, you do. But when you're engineering your automation system, you don't really want to have to wait for that. So what I did earlier is I actually booted up a couple of machines. And so Artemis runs in 4 stages. It has what's called the prepare stage, the execute stage, the teardown stage, and the publish stage. Notice it kind of runs like the test methodology I mentioned before. But we made it incremental. So what I did earlier, actually last night, is I kicked up 2 virtual machines that are also running in Iowa, already running. And what I'm going to do now is just literally run how fast is it to run VM-to-VM networking on these machines in Iowa. And so it's going to run this test called iPerf. iPerf is just a common measurement tool that's used out there for benchmarking networks. So it spins up, runs for 5 seconds, -- time equals 5, run my iPerf 5 seconds, and boom, it's done. It tells me 2 measurements here. So in Compute Engine, there's this thing called an external IP that you can run over and an internal IP. An internal IP is a machine data center IPv4 address, like a 10 dot address. And so you can see if you select an external address, it literally routes your traffic to the edge and back in. So from one VM, it's going to the edge of the Google network and back in. And for the data center address, the 10 dot address, it's literally going VM to VM. And so here I'm showing 2 gigabits per second on a 1-core VM. So this is an N1 standard 1. So I have 1 logical core running, and it's able to do 2 gigabits a second, machine to machine, which is the highest number in the industry, core for core. It's impressive. All right, so I'm going to switch back. So this is the provisioning. And then if I wanted to do the deep provisioning, I could just say run stage -- cleanup. But I'm not going to tempt the demo. I'm going to switch back, which I think I hit 1. All right. So with that, I showed you the automation that we run. And so how can you get involved? So here's what I would like to do next. We've obviously measured our own cloud. We've thought a lot about methodology. We've thought about a lot about workloads. How does that help all of you if you're trying to make decisions in the marketplace about where to put your automation systems? Well, what I'd love to do is for all of us to work together. Whether we use GitHub or something else, we can figure that out later. We want to obviously work across the industry. That means you. We want people to suggest or delete benchmarks. So there's been this notion in the benchmarking world that benchmarks have a version and they're done. I think things are moving much faster. To put benchmarks into a standards body and wait 3 years for something to come out is going to be a challenge. I think benchmarks should be more fluid. And this means we're adding and deleting things that are relevant as we think about cloud and as cloud is evolving. And this is sort of the last point, which was really we need to evolve benchmarks for cloud as the market evolves. We really don't know, honestly, where cloud is going. What I do know is most of what's going to be in cloud isn't here yet, and it's going to take all of you and all of everybody who's kind of watching online to move their workloads there. And as that happens, we'll understand it better, but we just don't know yet. So with that, I invite you to send me an email. I put it really small, vellum@google.com. If you're interested in benchmarking and want to try to do something that's more open and shared, we'd love to talk to you. So with that, thank you.
Thank you, Tony.
So I have a question from the moderator. In your presentation, you talked about benchmarking against different cloud providers. What about benchmarking the same application over time within Google Cloud to see if you can find regressions in Google Cloud?
Absolutely. So if you remember that pretty graph I showed you with the dashboards, that's literally what we do. So we run Artemis multiple times a day in and day out. Depends on the workload. Some workloads don't change that often. Some change a lot. And so it's continuously running. We actually use Jenkins to run the automation. Seemed like a really good tool, and so we just use it, and it goes and scripts around running Artemis, and then we publish all this data to our backends, which are all running on cloud. So yeah, good question. We definitely can find regressions, unfortunately. Any other questions?
Great.
All right.